In this video, we'll discuss about variability and how to measure it. Measures of central tendency yield information about the center or middle part of a dataset. However, businesses can use another group of analytical tools called measures of variability to describe the spread or the dispersion of a dataset. Using measures of variability in conjunction with the measures of central tendency makes possible for a more complete numerical description of the data. The key measures of variation are range. Range describes the difference between the largest and smallest data point in our dataset. Next, variance. The variance is the average of squared deviations about the arithmetic mean for a set of numbers. Standard deviation. Standard deviation measures the dispersion of a dataset relative to its mean. It is defined as the square root of the variance. Lastly, mean absolute deviation. The mean absolute deviation is the average of the absolute values of the deviations around the mean for a set of numbers. We'll start with the measure of range. Range describes the difference between the largest and smallest data point in our dataset. The bigger the range, the more is the spread of data and vice versa. A simple measure of variation is the simplest descriptive measure of variation for a numerical variable. The formula of range is quite simple. It is range equal to largest value minus smallest value in the sample. Calculating the range would further analyze the sample of 10 get ready times. We have already seen this dataset. To compute the range of this dataset, first we'll rank the data from smallest to largest as we have shown in the table here. As per the formula discussed earlier, the maximum value, which is 52, minus the minimum value, which is 29. The range is 23 minutes. The range of 23 minutes indicates that the largest difference between any 2 days in time to get ready in the morning is 23 minutes. The range measures the total spread in the set of data. However, the range does not take into account how the values are distributed between the smallest and largest values. In other words, the range does not indicate whether the values are evenly distributed, clustered near the middle, or clustered near one or both extremes. Thus, using the range as a measure of variation when at least one value is an extreme value is misleading. Now we'll discuss the measure of variance and standard deviation. Being a simple measure of variance, the range does not consider how the values are distributed or clustered between the extremes. Two commonly used measures of variation that account for how all the values are distributed are the variance and standard deviation. These statistics measure the average scatter around the mean, how larger values fluctuate above it and how smaller values fluctuate below it. A simple calculation of variance around the mean might take the difference between each value and the mean and then sum these differences. However, the sum of these differences would always be zero because the mean is the balance point for every numerical value. Thus, the calculation of variance requires to take square of the difference between each value with its mean and then sum those square differences. This sum of the square differences, called the sum of squares, forms the basis for calculating the variance and standard deviation, as we'll discuss shortly. For example, if a sample has a sample variance S square, then that square is the sum of squares divided by the sample size n minus 1. When we are working with population, the denominator n is the population size. However, we often work with samples and therefore we use sample size minus 1 as denominator. The sample standard deviation S is the square root of sample variance S square. Because the sum of squares can never be negative, the variance and standard deviation will always be non-negative values, and in virtually all cases, the variance and standard deviation will be greater than 0. Both the variance and standard deviation will be 0, meaning no variation, only for the special case in which every value in the sample is same. Consider a sample containing n values x1, x2 and so on up to xn. The sample variance S square is simply defined as the formula shown here, that is S square equal to x1 minus x bar raised to the power 2 plus x2 minus x bar raised to the power 2 and so on up till xn minus x bar raised to the power 2 summation of whole divided by n minus 1. Please notice that the formula for population variance is different from sample variances. For a population containing n values x1, x2, xn, the population variance sigma square is defined as x1 minus x bar raised to the power 2 plus x2 minus x bar raised to the power 2 and so on summation up to xn minus x bar raised to the power 2 divided by n, where n is the population size. Notice the difference between sample and population variances. In the population variance, we have capital N in denominator as compared to n minus 1, which is sample size in the context of sample variance. While the mathematical derivation of this is not required here, please observe that the difference between these two, the divisors, that is n and n minus 1, becomes smaller as the sample size increases and converges to large population size n. The formula of standard deviation and variance as discussed here can be further provided in a more compact manner. We can say this as shown here: s square equal to summation xi minus xi bar raised to the power 2 divided by n minus 1, and square root of that can be considered as standard deviation. This is a more compact form of the same formula provided in summation notation. And the formula for population standard deviation, that is sigma, can also be replicated in a similar manner. Again, here x bar is sample mean and equal to sample size. Xi is the ith value of the variable x. Xi minus xi bar is the summation of the square differences. Note that in both equations, the sum of squares is divided by the sample size minus 1 for sample and n for population. For now, and our understanding, that is, the sample estimate converges to population estimate as the sample size increases and converges to n. Let us illustrate the computation of sample for our 10 get ready times data. There are following steps that we'll discuss one by one, and they are also shown in the slide for our data, that is get ready times. As a step 1, we'll calculate the difference between each value and its mean. The mean is computed as 40, and the differences with each value are shown in second column as step 1. In the next step, step 2, we'll compute the square differences that are shown in the third column as step 2, and we compute the square differences for each observations. In the third step, we compute the sum of the square differences. The value is 412.4, and then we divide that by n minus 1, that is 45.82 becomes our sample variance. The square root of this number, which is 6.77, that is the standard deviation of the sample. The same steps can be replicated as shown in this slide to compute the variance and standard deviation of the population. Notice that everything remains the same except that the denominator that is being used here, the denominator is 10 instead of 9. Now we'll discuss the another measure of variability, that is mean absolute deviation. The mean absolute deviation of a dataset is the average distance between each data point and the mean. It gives us an idea about the variability in a dataset. The steps to calculate the mean absolute deviation are provided here. First step is calculate the mean. Second step is calculate how far each mean data point is from the mean using positive distances. These are called absolute deviations. Then these deviations are added in the third step. And in the fourth step, the sum is divided by the number of data points. This is also summarized in the form of formula below, which is MAD equal to summation xi minus xi bar divided by n. And notice that we are taking the absolute value of these differences. Let us try to compute these values for our get ready times dataset with 10 observations. The MAD measure for this data can be simply computed in those steps. In the first step, we'll compute the mean, that is 40, that is S1. Next step, we'll compute the mean differences of each observations, that is xi minus xi bar. This is our second step, S2. And the third step, we'll sum up all these values. The sum is equal to 50. And then in the fourth and last step, we'll divide this sum by the number of observations, that is 10. So we'll get our MAD value of 5. Till now, we have discussed the measures of variability, that is range, variance, standard deviation, and mean absolute deviation, MAD. In the next set of videos, we'll discuss different measures of shape. In this video, we'll start with Excel implementation of measures of variability. First, we'll discuss the measure of range, which is the difference between maximum and minimum value in a given sample. So the computation is quite easy. First, we'll compute the maximum value, which is 200, then minimum value, which is 80. Now the difference between these two maximum and minimum values is equal to the range of the data. In this case, it is 120. Similarly, if you look at another data, which is slightly modified version of this calorie data, where the extreme value is replaced by 1000 instead of 200, we can compute these measures, and let's have a look at these measures. Now the maximum value is 1000, and therefore the range has been extended considerably to 920. And therefore, if there are extreme outliers in the data, the range measure can increase a lot. Next, we'll discuss the Excel implementation of standard deviation and variance measure. We'll start by looking at the standard deviation and variance of a population, and then we'll compute the standard deviation and variance of the sample. So first, as a first step, let's compute the standard deviation and variance considering this calorie data as population. So for that, we need to have the mean of this data first. So we'll compute the mean or average of this data. Next, we'll compute the difference of each observation from the mean. Now we need to square these values in the next step, as we have already discussed in the previous videos. Then we'll compute sum of squares. Whether we are computing the standard deviation or variance of population or sample will depend upon this step where we are dividing the sum of squares by the number of values. So if I divide this sum of square by number of observations, that is count, there are 7 observations, this will become population variance. So this is my population variance. Instead of this, if I divide this number not by the overall count or size, but size minus 1, then they'll become sample variance. Notice, because of change in denominator, the value has increased. The standard deviation is nothing but the square root of this value. So it is easy to calculate. We can just write this simple formula SQRT to get the population variance. And in a very similar manner, I can get this is standard deviation of population, and in a very similar manner, I can get the standard deviation of sample by taking the square root of this sample variance. We can observe both of these values. There is also a very simple way to compute these values in Excel. So if I use this formula var.p, that will give me variance of the population, but it will be a more direct way, and you can see these numbers are matching with those calculated by us. Also, I can compute the variance of sample using this var.s. Now the sample version of this variance formula will apply. Notice it is same. And again, for the standard deviation also, I can use the formula for population, or alternatively, I can use the formula of sample. Generally, in real life, we do not have populations. We often work with samples, and therefore the formula that is the one with sample is more applicable in real practical situations. Next, we'll discuss the Excel implementation of another important measure of variance, which is mean absolute deviation. So we'll compute mean absolute deviation. The computation is quite easy. First, we need to compute the mean of the data, which is average formula. Now we'll compute the absolute value of mean differences, which is abs deviations. So these are my absolute deviations from the mean. We'll compute all these deviations. These will be positive because we are computing absolute values, and then we'll sum them up to compute the absolute deviation. This is the summation of all the deviations, and now we need to average it out by dividing it with number of values in the sample. So we get a value of 37. So this is mean absolute deviation of the sample. In this video, we'll discuss the R implementation of measures of variability. We'll continue with our existing data, which is calorie data from cereals. A brief description of this data is provided on the console. When I run this data with my control enter command, notice the data is populated on the console window. It starts from 80 and up till 200. As the first step, we need to compute the range of this data. That is our first variability measure. Now I can check the range of this data by simply running range command, which will give me the lowest and highest values in the data, that are 80 and 200. If I want to see the range, I can simply compute the maximum value of this data and subtract the minimum value of data from this to get the range, which is 120. So this was our range computation. This was our range measure. Next, we'll try and compute the variance and standard deviation measures from the data. As a first step, I'll show you how to compute the variance of the data. Simply var command, data and calories. This will give me the variance of this data, which is 2200. But please notice, this is sample variance, that is sample var. So this is my sample variance. In order to compute population variance from this data, I need to multiply this data from its denominator, that is -1, and divide it by the length of the data. This will result in the population variance. I can assign this value to a new variable as well, that is population var or population variance alternatively, and store it in this new variable. Notice, if I want to extract this value from population var, I need to simply just select this population var variable and press Ctrl Enter on this to get this value, which is 1885.7. All these values are appearing in my console window. Similarly, I can compute the standard deviation, which is quite easy. I can use this SD command, standard deviation and data $calories. This is the standard deviation of the data. I can assign this to a new variable as sample SD, which will be the sample standard deviation of this value. However, in order to compute the population standard deviation, as we did earlier, I need to multiply this with the square root of the factor, which is length of the variable -1 divided by length of the variable, which is adjust for the population part. So if I run this, I'll get the sample standard deviation, which is 43.42, which is different from 46. I can assign this to a new variable, which is population standard deviation. If I want to extract this variable, I can simply take it out and run Ctrl Enter to get the value of population standard deviation. So this is my variance and standard deviation measures for population and the sample. The last measure that we are going to compute is our mean absolute deviation. Mean absolute deviation measure, or you can say MAD measure. As part of MAD measure, it's quite easy. First, I'll do the manual way or a slightly more complicated way. So what we'll do is we'll take our data, subtract the mean of the data. Mean of this data is, as we remember, it is 130. So we'll subtract the mean from all observations and we'll compute the absolute value of these, which are populated on the console window. Now what we need to do is we need to sum up these absolute values and then divide them by the length of the sample, that is data.calories, $calories, and we'll get the MAD value. Now this was a slightly lengthier and more complicated way. A more easier way is to use matrix package. So first, if you have not installed, you need to run this command matrix. Since I've already installed matrix package in my current working library, for installation of library and installing in their current working environment, that is already discussed in the previous videos. So we'll not explain that in detail here. So we'll simply put the library matrix in our current working environment. That is quite easy. Once I have put it, now I can use the functionalities, and a very important functionality is this MAE command. If you want to know more about this MAE command, you can simply type $MAE, and notice this MAE gives you the absolute difference between vectors. So what I can do is I can simply write this MAE, then I'll use my vector of data, which is data $calories, and then I can subtract it from the mean value, which I've already computed. And this will be my mean absolute error or mean absolute deviation here in this particular case, which is, just check here, small error. Okay, so I'm just running this. Instead of minus, I need to put comma. So now I'll get the same value. So this is my mean absolute deviation. So this is how you compute the mean absolute deviation directly using the R functionality from matrix package. In this video, we'll discuss about measures of shape. The measures of shape is a tool that can be used to describe the shape of a distribution of data. In this video, we'll examine two measures of shape, that is skewness and kurtosis. Skewness refers to a distortion or asymmetry that deviates from the symmetrical nature of data around its mean, while kurtosis measures the peakedness of the curvature of data around the distribution. The distribution of data in which the right half is the mirror image of the left half is said to be symmetrical. One example of symmetrical distribution is the normal distribution or bell curve. Here, skewness is a property where distribution is asymmetric or lacks symmetry around its central measure, like mean, median, or something like that. Skewness measures the extent to which the data values are not symmetrical around the mean. There are three possibilities. Either mean is less than median. This is called negative or left skewed distribution as shown in panel A. Then you have mean equal to median, which is symmetrical distribution, zero skewness as shown in panel B. And then you have mean greater than median, where you have positive skewness, that is right skewed distribution as shown in panel C. In a symmetrical distribution like panel B, the values below the mean are distributed in exactly the same way as the values above the mean, and the skewness is zero. In a skewed distribution, there is an imbalance of data values below and above the mean, and the skewness is a non-zero value, that is less than 0 for left skewed distribution or greater than 0 for a right skewed distribution. Panel A displays a less skewed distribution. In a left skewed distribution, most of the values are in the upper portion of the distribution. Some extreme small values cause the long tail and distortion to the left and cause the mean to be less than the median. Because the skewness statistic for such a distribution will be less than 0, some use the term negative skew to describe this distribution. Panel B displays a symmetrical distribution. In a symmetrical distribution, values are equally distributed in the upper and lower portions of the distribution. This equality causes the portion of the curve below the mean to be the mirror image of the portion of the curve that is above the mean and makes the mean equal to the median. Panel C displays a right skewed distribution. In a right skewed distribution, most of the values are in the lower portion of the distribution. Some extremely large values cause the long tail and distortion to the right and cause the mean to be greater than the median. Because the skewness statistics for such a distribution will be greater than 0, some use the term positive skew to describe this distribution. Next, we move to the kurtosis measure. Kurtosis measure the peakedness of the curve of the distribution. That is how sharply the curve rises approaching the center of the distribution. Kurtosis compares the shape of the peak to the shape of the peak of a bell-shaped normal distribution. That is bell-shaped normal distribution, which by definition has a kurtosis of 0. A distribution that has a sharper rising center peak than the peak of a normal distribution has a positive kurtosis, a kurtosis value that is greater than 0, and is called leptokurtic. A distribution that has a slower rising, that is flatter center peak than the peak of a normal distribution, has a negative kurtosis, a kurtosis value that is less than 0, and is called platykurtic. A leptokurtic distribution has a higher concentration of values near the mean of the distribution compared to a normal distribution, while a platykurtic distribution has a lower concentration compared to a normal distribution. In affecting the shape of the central peak, the relative concentration of values near the mean also affect the ends or tails of the curve of distribution. A leptokurtic distribution has fatter tails, many more values in the tails than a normal distribution has. When analysis mistakenly assumes that a set of data forms a normal distribution, that analysis will underestimate the occurrence of extreme values if the data actually forms a leptokurtic distribution. Some suggest that such a mistake can explain the unanticipated reverses and collapses that financial markets have experienced in the recent past. We'll discuss the implication of these shape measures and kurtosis skewness with R and Excel. In this video, we'll discuss the R and Excel implementation of our measures of shape. First, let us discuss the implementation of measures of shape, that is skewness and kurtosis, in Excel using our get ready data, where we have times observable for getting ready in the morning. To compute the skewness, we'll simply use this skew functionality in R. And the skewness of this data is 0.085, which seems that it is positively or right skewed data. For a symmetric distribution, the skewness should be equal to 0. We can also generate the kurtosis of this data, and the kurtosis of this data is 0.1. Please note that this is a relative kurtosis measure. That means Excel functionality computes the kurtosis relative to normal distribution. Normal distribution has a kurtosis of 3. So there we have an excess positive kurtosis with this time to get ready data, that is 0.13. So absolute kurtosis would be 3.13. That means it has a positive kurtosis, excess positive kurtosis. Now we'll discuss the implementation of shape measures with R. We'll carry on with our calorie dataset with cereals. So this was the dataset. We can see that dataset in our console where I have populated it. First, we need to install some of the packages, relevant packages. These are TCDs and movements. Since I have already installed these packages, I will not run these commands. I'll simply put them into my current working environment, which is first for TCDs and then for movements. Now I have installed or both of these libraries, both of these packages, TCDs and movements in my current working library. So I'll start by computing the skewness of my data, which is calorie data. Notice the skewness. The skewness is turning to be 0.65, which is a positive skew as compared to normal distribution, a symmetric distribution like a normal distribution, which has a 0 skew value. Similarly, I can compute the kurtosis for this data. Notice the kurtosis for this data is 1.807, which is less than 3. That is normal distribution, or a distribution like normal distribution has a kurtosis of 3. So it seems it has a peak which is lower than a normal distribution. Now, if you want to know exactly how it works for normal distribution, we'll generate a normal distribution like this. Generally, we use rnorm function. If you want to know more about this rnorm function, you can simply put question mark and see all there is to know about this rnorm. It will be populated in the help window. We can check that. What are the syntax and parameters to be fed? So first, let us generate this normal distribution, and that is rnorm will probably 10,000 values, and the mean is 0 and standard deviation is 1. So our normal distribution is there. Now we'll compute the skewness of this distribution. Notice that this value of distribution is not exactly 0, but it is very close to 0. It is linked to the number of values we provide. For example, if I decrease the sample size, I put it to 1000, you'll notice the skewness is slightly more in magnitude. Although it is positive, but it is more in magnitude. If I increase the number of observations in the sample, the skewness will go down in terms of magnitude. Sign doesn't matter much here because the magnitude is quite low. Similarly, if I'm talking about kurtosis and I'm using reasonably large sample, then the kurtosis will be closer to a normal distribution, which is close to 3. If I decrease the sample size, notice the kurtosis value will also not be as close, slightly different from 3. And as I increase the observations, maybe very large number of observations, then in fact you notice that it will be very close to 3. So the kurtosis of a normal distribution is 3. And of course, the kurtosis and skewness of our data, which is calorie data, is not same as normal distribution. That means it is not exactly symmetric because of skewness measure and not exactly same peakness as normal distribution.